in this lesson, we now want to look at the connection between coding and entropy. So in which sense does entropy allow or put limits on the design of codes? And in this first lecture, we will see that indeed the entropy can be seen as the theoretical lower limit that a code can achieve in sense of its efficiency regarding the length of code words. So in the previous lesson, we have seen that Kolmogorov complexity, so the Kolmogorov complexity of a string, can be seen as the length of an optimal code for sigma. So optimal code in the sense that it's an optimal code for, or input for, the universal prefix-free machine, or in the case of plain complexity, an optimal program or code for just a universal machine. So now in this lecture, we want to see if an analog interpretation holds for the probabilistic setting with regards to probabilistic entropy. So here's the setting that we have for this lesson. X is an A-valued random variable. A, as usual, is a finite set. We want to assign code words to each outcome of X, so to each element in A, so that the expected code length is minimal. So formally, we define a source code, or just code, for the random variable X to be a mapping C from the values of X, right? So A, to the set of strings over a finite alphabet D. And in the following, to make notation a little bit easier, we identify D with its cardinality. So essentially, we just think of D as the set 1 to D. Abusing notation here a little bit. And then the expected length, L of C of a code, is with distribution P, is given as just the expected value of the code length, right? So here we have code, this is the code word for A, right, for outcome A. This is the length of it, and then we just multiply the length by the probability. So it's the expected length L of C. So let's look at an example. The idea is, of course, to design codes as efficiently as possible, meaning that the expected length of a code word is as short as possible. Well, to do that, of course, we have to assign to symbols in X, or outcomes that occur with high probabilities. We have to assign short code words, right? So assume we have the following random variable. Our set A has 4 outcomes, and the probability of outcome 0 is 1/2. Of 1 is 1/4, the probability of outcome 2 is 1/8, and outcome 3 also 1/8. And we want to design a binary code for this random variable. One way to do this, of course, since we have 4 outcomes and only 2 possible symbols in our coding alphabet, well, just assign every symbol in here, every outcome in here, a 2-string or 2-bit code word. So 0 to 00, 1 to 01, 2 to 10, and 3 to 11. Then, of course, the expected code length is 2, right? Because every code word has length 2. But this code does not take into account that the outcomes here have different probabilities. So an outcome of relatively low probability, such as 3 here, gets the same length code word as the outcome of the highest probability, 0. Compare this with this code C2 here, where we actually map 0 to the shortest code word, and the code of lowest probabilities, the two words with or outcomes with lowest probabilities, to the longest code words. So this code has expected code length 1/2 times 1, 1/4, right, times 2, 1/8 times 3, and again 1/8 times 3. So altogether that gives 1.75. And if you compute the entropy of the random variable, right, with this distribution, you will see that the entropy of x is exactly the same. It's also 1.75. So is this a coincidence, or is there something more behind that? Well, as you may think, suspect already, there is a close relationship between code length and entropy, and we want to find out what exactly the relationship is. So let's set a few technical details. A code C is called non-singular if it is 1-to-1. So a non-singular code suffices, of course, for an unambiguous description of a single value of x. Right? If I have a 1-to-1 mapping, then from a code word I can uniquely decode which value of x was coded by it. And the codes we saw in the examples, of course, had that property. So that's, of course, a desirable property of any code. But we actually want to do a little bit more. We want to not only encode single values of x. I mean, since we're in the probabilistic setting, we're actually looking at asymptotic behavior here. What we want to do is actually to encode data streams produced by our random variable. So in other words, we want to encode whole strings over the alphabet A, or even sequences, infinite sequences. Well, to that end, we look at the extension of a code C. It's denoted C star. And now here we have an A string, right? A finite sequence of symbols from A. And we just say the extension C star of our code to sequence strings, and also sequences possibly, is just the concatenation of the code words that are assigned to each of those values here in the string. And we say that a code is uniquely decodable if its extension is non-singular. So that means we can, whenever we have a sequence of concatenated code words here, we can from that reconstruct the input string. There are various ways how one might ensure that a code is uniquely decodable, but we've already encountered this problem when we were talking about Kolmogorov complexity, and then came to the idea of a concept of prefix-free complexity, where we exactly had this problem that we could not tell apart two concatenated codes, right? So one way to ensure this is actually to make sure that or require that the code words for C form a prefix-free set. And if that's the case, then we also talk about or speak of a prefix code, or you also find the notion of instantaneous code. Instantaneous because you don't need to read the whole code word to reconstruct just an initial segment of it. Once you've seen it, and because of the prefix freeness, you can reconstruct this bit by bit, so to say. Well, we now come to one of the fundamental restrictions and results about for prefix codes, which is the Kraft inequality. The Kraft inequality puts an essential restriction on the way we can design prefix codes. So the theorem is as follows. Suppose we have a prefix-free set, subset, so a prefix-free set of strings over the alphabet D, our coding alphabet, and it's possibly infinite, right? Then the sum over d to the minus length of sigma of all sigma in W is at most 1. So if we have a prefix code, that means that the d to the minus the length of the code words together, the summed up, is at most 1. So it cannot exceed 1. That's one restriction. On the other hand, conversely, if we have a sequence L0, L1, L2 of non-negative integers that satisfies this, right? So think of those are as length as possible, or intended lengths for code words. If they satisfy this restriction here, then we can find a prefix code. So a prefix-free set of code words, sigma 0, sigma 1, and so on, of strings over D, such that the length of the ith string is just Li. Right? So it's a sufficient and necessary condition, so necessary and sufficient condition for the design of codes. So the proof of Kraft's inequality is relatively simple. We start with the necessary direction. So we have a prefix-free set, and we want to show that the sum of d to the minus the length of the code words, or the strings in the prefix-free set, is at most 1. How do we do that? Well, we just argue measure theoretically. So let lambda be the measure on the space of infinite sequences over D, induced by setting the measure of the cylinder set induced by sigma as d to the minus the length of sigma. Right? We encountered that before, right? It's just to keep it easy, just assume that D is just the binary alphabet, right? Then we have our string here, sigma, right? Then this induces the cylinder set, and the measure of the cylinder, the uniform measure, was just 2 to the minus the length of the cylinder set. So now if we identify a string with the cylinder it induces, a prefix-free set corresponds to a disjoint collection of open sets, right? If we have now several strings in a prefix-free set, we look at the cylinders, well, then this will be a disjoint collection of open sets. But then we can just use the countable additivity and the monotonicity of the measure that we just defined, right? And just say that the sum of 2 to the minus length of sigma, so here I already assumed that D is binary. So in the general argument, you should probably replace this by D. But now you can use the countable additivity. We have a disjoint collection of open sets that together give an open set, right? But countable additivity means the measure of the disjoint union is just the sum of the individual measures. But now this set here is just an open set sitting inside the whole space that has measure 1. So by monotonicity, this measure is at most 1. So once we transferred the setting, or this problem, into a measure setting or framework, it becomes a very easy argument using the nice property of prefix freeness and the connection to the topology on the Cantor space, right? So then it becomes a very easy argument indeed. So for the opposite direction, we can explain this best using a diagram. So first we assume that the length that we want to achieve as the length of a prefix-free code are ordered. So from smallest in increasing length. So L0, L1, L2, and so on. The idea is now to use this ordering to pick out strings from the left in a prefix-free way. So whenever we pick a string, we pick the next one that is not a prefix or an extension of the previous one immediately to the left, corresponding to the length here. So we would start with a string of length L0. That's the leftmost possible, and since we have not chosen a string yet, so that would be just the string all the way to the left. So this would be sigma naught of length L0. So this would be length L0. So then in the following parts of the construction, we of course now cannot choose any string that is an extension of sigma naught. So now that we have chosen our string of length L0, so L0 gets a check mark here, we pass to the next length, L1, and we choose the leftmost string that is still possible, right? So that's not in this cylinder here, that is of length L1. So that could look like this. So then this would be our string sigma 1, and it would have length L1. Then of course in the further course of the construction, this cylinder here now would be forbidden. Right? We cannot choose any extension in there. So now in the next step, we would take the leftmost, or find the leftmost string to the that is still possible of length L2, and that will be our string sigma 2. So now assume we have chosen our prefix-free, in a prefix-free way, our string sigma naught, sigma 1, sigma 2, up to sigma n, where the length of sigma I is L of I. Now, how much measure do we still have? So how much free measure is there? So free measure in the sense that how much space here, how much space do we still have left to choose our next string, sigma n plus 1? Well, the free measure, right? So how much measure do we have used so far? Well, we've used, assuming we're working in the binary case, binary alphabet case, is 2 to the minus length sigma naught plus all the way up to 2 to the minus length of sigma n. But by the choice of sigma naught, remember sigma naught was chosen of length L naught, sigma 1 was chosen of length L1, and so on. So that's the same as 1 minus 2 to the minus L naught plus blah 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 2 to the minus Ln. Now the assumption was that the sum of 2 to the minus Li for all I, so this here sums over all I, not just the first n ones, the sum of 2 to the minus Li over all I is less than or equal to 1. So in particular, this means that this here is greater than or equal to 2 to the minus Ln plus 1. So we do have enough measure to accommodate a string of length Ln plus 1, right? And since we've chosen our previous strings always adjacent, we know that at level Ln plus 1, there must be one free string. So now let's assume here we have level Ln plus 1. There must be one free string here. So this set here is not a fragmented set. It's just like one giant block, and we have 2 to the minus Ln plus 1 free space at least, so we can find our extension here, our next string up here, sigma n plus 1 of length ln plus 1. And then we can carry on this argument inductively, of course. So I recommend that you really formally check that this construction works. So the trick here is to kind of first order our length, and then we can choose these strings in this leftmost, picking the leftmost possible string next, so that here we have one block of strings, so there's no fragmentation, so we can always choose have enough a free block of the according to the measure that we at least have left over. So the Kraft inequality puts some restraints on the nature of a prefix code. So we can only find a prefix code if the lengths that we assigning to our code satisfy the Kraft inequality, right? So now, subject to this restraint, what is the minimum expected length of a code for our random variable x? So suppose we have our alphabet A, and we now abbreviate the distribution P of x being probability of x being equal to I as just P sub I. And we want to find code lengths L1 up to Lm such that we minimize this, which is the expected code length L, over all integers L1 up to Lm satisfying the Kraft inequality. Note that the Kraft inequality, as we stated it, actually works also for infinite set of code lengths. But here we are now, in particular, it means it also works for a finite set of code lengths, which we apply now here. So we now assume we only have a finite set of code lengths. We can get a pretty good estimate or idea of what the minimum expected code length should be using calculus. And in order to do that, let us relax the restrict condition on the Li a little bit. Instead of requiring them to be integers, just let them be non-negative reals. And also assume that the constraint holds with equality, so that the sum d to the minus Li is actually 1. And then we're in the situation of trying to minimize a function, a multivariate function, subject to a constraint here. And for that, there exists techniques from calculus, namely the technique of Lagrange multipliers. So this technique of Lagrange multipliers tells us, in order to minimize the function subject to a constraint here, we have to find the critical points of the partial derivatives of this auxiliary functional capital lambda, which is the sum of the pi li. This is the function, the multivariable function we actually want to minimize, right? Plus this parameter lambda multiplier, lambda times the restriction here written as in this form. So let's see what the partial derivatives are like with respect to Li, which is our variable, right? So d lambda over dli is just, as you see here, pi minus lambda times what here the derivative of this term for Li is d to the minus Li times logarithm, the natural logarithm of d. Now we have to find the critical values of the partial derivatives, so we put this expression to 0 and then solve, and we obtain that d to the minus Li is equal to pi over lambda times log d. So now we put this finding here, so this identity, back in the original constraint, this equation, right? So, and then we obtain that the sum of the pi is equal to lambda ln d, so which means lambda is 1 over ln d. But now plugging this back into here gives us that d to the minus li is equal to pi. And thus now taking logarithms means that the optimal length here, li, l star I, is just the negative logarithm with respect to base d of pi. Right? So we just take logarithm here, logarithms on both sides, and we get that li, right? So this is the critical point here now, that is equal to a negative logarithm with respect to base d of pi. Now if we plug those back into our original function that we minimize, well, the critical value is li star, well, then we get l star is equal to pi li star, which is now minus pi log d of pi, which is just, as you may recognize already, is just the entropy. And now the entropy with respect to the log now to base d instead of base 2. So usually we had base 2, but now we're working with an arbitrary finite alphabet of size d, so we replace the binary logarithm by the logarithm with respect to base d, and that we denote the entropy then by h sub d of x. But the fundamental insight now is really the optimal length is given as the entropy of the random variable with respect to the cardinality of the alphabet. Well, strictly speaking, it's too early to say that this is really the optimal length. Those are just the critical points, right, for which the partial derivatives vanish. But that's only, as usually in calculus, it's only a necessary condition for minimum to occur. So strictly speaking, now we have to verify that this is actually a global minimum here. These li stars actually do constitute a global minimum for l star. And one could do this either via calculus again, right? So looking at the Hessian and stuff like that. But one can also verify this directly using different methods. So, and that's what we want to do here. So we want to verify directly that the previous bound is indeed a global minimum. No integer length prefix code has expected length less than the entropy. So here's the theorem. So let L be the expected length of a d-array prefix code of a random variable. Then L is greater than or equal to the d entropy of x, where equality holds if and only if the values of d to the minus li are exactly the pi, exactly the probabilities, the distribution of the random variable. And the proof is actually not that hard. So we want to estimate L minus h of x. So in particular, we want to show, so the goal is to show that this here is greater than or equal to 0. We just plug in the definitions. So L was given as the expected code length, and entropy is just given as this. Right? So note here, the minus plus the minus from the entropy turns this into a plus. So now we replace, a little trick here, we replace Li by log d of d to the minus Li, which then makes us able to kind of contract the logarithm here, because now we have identical bases, and the pi's here are also the same on both sides. Before we do that, though, we define the following values here. We set c to be the sum of the d to the minus li, and r sub I to be just d to the minus li over c. So think of this now, this is the c is the overall mass that is given to us by the li's with respect to our base d, right? And ri is then just the mass that the length li contributes to the overall mass. So you can think of this as the probability distribution induced by our code length. So we have the probability distribution of the random variable, which is given by the pi's, and now we have the kind of distribution that is given by the code lengths, right? So this is to normalize it, and then this is the probability of the assigned to or corresponding to the ith code length. So using these definitions here, we can rewrite this expression as follows. So the pi log pi moves over here. And then we have this minus pi log d to the minus li. Now this we write as minus pi log d to the minus li over c times c, right? But this term here, by our definition, is just ri. So now we can pull this together. So now look, contract the logarithm here, right? And get pi log d pi over ri, right? Because we have minus log ri, so it's pi over ri plus the log that remains here from the constant factor c. And after we contracted this log d pi and log d ri over here, we're just left with some pi c. The pi's are a probability distribution, so they sum up to 1, right? So we just get log d of c. Now if you look at this expression here, this should look familiar, right? That's the Kullback-Leibler distance. So this is the KL distance or divergence. Only with the only difference here is that we have a log d instead of the binary logarithm, which we used in the original definition. So that just factors out as a 1 over log d here, times the Kullback-Leibler divergence of the distributions pi and ri. So the distribution of the random variable versus the distribution of our code lengths, plus our factor log d1 over c. C, note, however, is, so c is at most 1. So this here will be a negative value. So log dc is negative or 0, or in turn this here log d1 over c is positive. We've also shown in the previous lecture that the Kullback-Leibler divergence is always greater than or equal to 0 using Jensen's inequality. So the whole term here will be greater than or equal to 0, which is just what we wanted to show. And it also follows from the results of the about the Kullback-Leibler divergence that this is equal if and only if so this is 0 if and only if the distributions are equal, right? So and then this in turn yields that these so the statement, the second statement of the theorem, namely that we get equality, right? L is equal to hd of x if and only if our d to the minus le distribution here is equal to the pi's. So this finishes our proof, and we have indeed shown now that the entropy, so the d-entropy of our random variable, is in fact the lower bound, so the optimal code length that we can achieve in a code for our prefix code for our random variable x.